So what is it that makes an acid? What is it that makes it unique? What makes it different than a base? Why is a base and not just any other ionic compound? That's what we're going to be looking at over the next few slides. For this class, we use Arrhenius's definition to look at the structure of what makes an acid and a base a base. Now, there are other definitions, and if you take Chem 2, we talk about some of those other definitions. If you take organic, you'll talk a lot about Lewis acids and bases. But for us, Arrhenius's definition is a really great one, and it's pretty simple to understand. Now, a little bit about Svante Arrhenius. You know, I love to talk about the scientist. He was working on his dissertation to get his PhD back in 1884. And he was looking at how ionic compounds, when they are solid, they do not conduct electricity. But when you put them in water, when you dissolve them, all of a sudden they can conduct electricity. And this was very unique. It was not well known, this idea of electrolytes at that point in time. Now, his professors weren't really impressed. They actually gave him the lowest possible passing grade. Savante, he wasn't too worried about that, though. He went on, did a little more research, ended up getting a Nobel Prize for this same exact information. It's crazy. So never lose faith in yourself. What he decided, or how he defined what an acid and a base is that an acid is a substance that reacts with water to produce what's called the hydronium ion. So here's that hydronium ion. Hydronium is H3O plus. So it looks like water, but it stole an extra hydrogen. Now in chemistry, we tend to get really lazy, and instead of actually writing it as H3O plus, a lot of times we just write it as H plus. A base is a substance that produces hydroxide ions in water. Okay, do you remember what hydroxide is? Hydroxide is OH negative. Now, one of the limitations that this particular definition has is that everything has to be in water. It's not necessarily the best to have that limitation. But again, it works really good for what we're going to be looking at. So I like this definition. It's pretty simple. Your acids will generally always start with hydrogen. Your bases generally will end with OH, with a few notable exceptions that we'll end up talking about. So what happens if you take an acid and add it to a base, if you mix them together? Well, that's called a neutralization reaction. So in general, the reaction of an acid plus a base, we can predict the products. We're going to produce water, and you produce some sort of ionic compound. Okay, ionic means that it's a metal and a nonmetal, so remember that. So you can say that acid plus base gives you water, and then we have this new name for that ionic compound. We call it salt. So salt is not just table salt, it's not just sodium chloride. Salt is any ionic compound that doesn't contain hydroxide or oxide. Hydroxide and oxide are both used in bases. So that's why we kind of eliminate those. We set them off to the side where they said, okay, these are probably bases, but if it's anything else, we can also use this term salt. So I have a few examples. They're in the middle of the page. Let's see how your naming goes. So NaCl is sodium chloride, KBr is potassium bromide, and Li2SO4, don't let that little, oh crap, there's 3 or more elements in there. It's got a polyatomic ion, it's lithium sulfate. Now you might say, wait a second, that ends with oxygen, isn't that a problem? Well, no, because it's inside of a polyatomic ion, so it's fine. Lithium sulfate. Down on the bottom, again, we have this generic idea. Make sure to know this one. Acid plus base goes to water plus salt. At the very bottom, it talks about that, it gave an example of this type of reaction. And this is actually just a metathesis or double replacement reaction. Let me show you. So here we have HCl, and we have sodium hydroxide. Now what'll happen is that the H is going to come over here and react with the OH. H is +1, OH is -1. I often like to write this as HOH. It's just water. You could write it as H2O. It means the same thing. It's just for me, as I'm writing it out, to make me really understand it's a metathesis reaction, a lot of times I'll write it like this. Now the other thing that's going to happen is that the sodium is going to come back and is going to get that chloride. Sodium, watch your charges, is a +1, chloride's a -1. It's going to form sodium chloride. So this is a double replacement reaction. So if you want to identify an acid just by looking at it, acids are molecular substances. So molecular means it's two nonmetals. In particular, an acid, based on the definition we've talked about so far, will have hydrogen, and then it'll have some other nonmetal. So maybe hydrogen and chloride, hydrogen and sulfur, hydrogen, sulfur, and oxygen, something like that. It's going to react with water to form hydronium. Now, what happens there is that the water goes over and it steals away the hydrogen, and it leaves behind whatever else it had. So we can say that the acid plus water gives hydronium plus an anion. Ooh, do you remember what an anion is? That just means something with a negative charge. So we can write this generically. We can say HA. Now HA is like I said, it's a generic acid. It's a made-up acid. It's a happy acid. It's hydrogen and an anion. And along comes water, and water is going to steal that hydrogen away, and it leaves the anion. Now in chemistry, we tend to get lazy. Like I've already mentioned, sometimes we'll write this as HA dissociates to H plus A minus. So you'll often see that, where instead of writing hydronium H3O plus, instead of actually showing that we're reacting this with water, we kind of jump ahead and say, hey, they split up. So we have an example. We have hydrogen chloride hydrochloric acid reacting with water to form hydronium and the chloride ion. So the H and the Cl split from one another. Now this is an example of an ionization reaction. That just means that we're forming ions where we started with no ions, where we started with something that was just molecules. And on the bottom, we have some nice little pictures of what's happening molecularly. So here's our HCl. So we have our little white hydrogen. There we have our chlorine. Along comes the water, and water says, oh, I'm going to steal that hydrogen away. And so the hydrogen pops off that HCl. We form hydronium, and then we're left with the chloride ion. Well, you might ask, well, how many hydrogens will it react with? Well, that's all based in the name. So we have something called monoprotic acids. Monoprotic acids furnish just one hydrogen per molecule of the acid. An example of that, this is acetic acid. This is also the one that's shown over to the side. Now notice acetic acid is written really weird. It has the H in front, and then it has the C2H3O2. The C2H3O2 is the polyatomic ion. But there's only one hydrogen out front. So even though it has extra hydrogens, there's only one hydrogen that's available to be stolen by water to form the hydronium ion. So that's how we know that this is a monoprotic. Again, that's going to give one hydrogen, one H plus per molecule. Now, that's not the only type. We have what are called polyprotics, and we know that the prefix poly means many. So this furnishes more than one. So within this idea of polyprotic, we could talk about diprotic, and diprotic would have two. Now this will actually happen in two different steps. So this is sulfuric acid. Now notice that there's two hydrogen right up front, and what will happen is that a water comes along and it says, oh look, there's some hydrogens, and it steals one of those hydrogens away. That leaves the hydronium ion. And then looky here, we have HSO4 minus. So we took away one hydrogen, So we took away something that was positive, so it left it with a negative charge. And then water says, oh, look, there is an HSO4 minus molecule. Let's steal another hydrogen. And it does that, and it leaves sulfate. So if there's two hydrogens, it's called diprotic, and it happens stepwise. Well, let's keep going. We can also have something called triprotic. Triprotic furnishes 3 hydrogens for every molecule of that acid. Just remember, this will also happen in a stepwise fashion. So we talked about acids. Well, now we have to talk about bases. Bases can be categorized into 2 areas. We can have ionic bases and molecular bases. Ionic bases are by far the most common. These are any ionic compound that contain hydroxide or oxide. So remember, salt was any ionic compound that doesn't have hydroxide or oxide. A base has hydroxide or oxide. Again, this is a very limited definition of acids and bases, but it works well for this class. So you would expect to see a compound ending with OH or just O oxide by itself. Remember, these are ionic, so metal and nonmetal. Examples, we have a few right here. Let's see how your naming goes. NaOH is sodium hydroxide, and then we have calcium hydroxide, and then we have calcium oxide. Now we also have something called a molecular base. These are pretty unusual. In fact, we only really go over one in class, and that's ammonia, NH3. And what makes this a base is that if it's put with water, and that's what's showing here at the very bottom, they collide, and that ammonia will steal a hydrogen away from water. And so that actually leaves the OH ion, the hydroxide ion. This is kind of complicated, especially when you start looking at the different reactions. Just remember that we do have a molecular base called ammonia, and you'll see that time and time again.